Welcome learners in the series of videos on topology, and this is video number 61. In the previous video we talked about Henn-Borel theorem and some related corollaries. Okay, so in this theorem we will prove a statement of a theorem or something called as Lebesgue covering lemma. Okay, so let's put up that first. Lebesgue covering lemma. So we will study this today and we will prove this. Okay, and then in the next video we will talk about some related concepts. Okay, lemma. Lebesgue covering lemma. So let me first state the theorem. The lemma. So understand the statement. Let X be a sequentially compact metric space okay, then for every open cover, say let us take a cover, say U alpha indexing set I, so alpha belongs to I, there exists delta greater than 0. Now of course remember that this delta depends on the cover. Okay, so let me put that in the bracket. Depending on the cover, depending on the cover, it depends on the cover. So for every open cover there exists delta greater than 0 such that for all subsets A of X with diameter, now let me write a diameter, not delta. I hope you know the definition of diameter that comes from the metric spaces. Okay, so if you don't know that, please check, at least that you can do. So diameter of A is less than delta. So you take any subset of X whose diameter is less than delta, there exists some element in indexing set, say alpha A, that is denoted by alpha A based on this A, alpha A belonging to I, such that this A will be contained inside U alpha A. Okay, what it says is if you take any open cover and based on that open cover there exists some delta greater than 0 such that if you take any subset A of X whose diameter is less than this delta, then there exists some element in this open cover such that A can be put up inside that element, right? A is contained inside U alpha A. Okay, so let me ask you, pause the video and write the negation of this statement. Write the negation of there exists delta greater than 0 such that something happens. Okay, so write the negation of the statement from here to here, and then we will proceed with the theorem. Let's move ahead. Let us do this proof. Now to show that this happens, let us take a cover first, right? We need to show that every open cover U alpha belongs to I, something happens. So let us take a open cover. Let us take some arbitrary open cover. So let U alpha belongs to I be an open cover for X. Open cover for X. Let us take an open cover. Now, for this open cover, we need to show that there exists delta greater than 0 such that something happens. Okay. Let us go by contradiction. Suppose this does not happen. Okay. So suppose that there is no delta, there is no delta greater than 0 satisfying the requirement of the statement. What does that mean? There is no delta which will satisfy the requirement of this statement. So that is what the negation talks about. That is, this implies there is no delta means for all negation of this, there exists delta greater than 0. That means for all delta greater than 0, no matter what delta you are taking, we are saying that for all subsets A of x. So let us take a subset. There exists, say, A delta subset of x such that whose diameter is less than delta. Diameter of this A delta is less than delta, and this is not true. This is not true means you take any element of U alpha, element of this cover, A will not be contained inside that element. Okay, how to write it? And for all alpha belongs to I, this A delta will not be contained inside U alpha. Okay, let us mark this equation. Let us mark this as star. Okay. Now, in particular, what happens? We said that for all delta greater than 0, something happens. So, in particular, if we take natural number, so in particular, say if we take natural number, say for all n belongs to natural number, we can take a set 1 upon A of 1 upon n will not be contained inside U alpha for all alpha belonging to I. This delta greater than 0 can be anything. So let us take for natural number 1 upon n, which is always positive. So A 1 upon n will not be contained inside U alpha for all alpha belonging to I. Okay, so let us take one point from this A alpha. Let us take one point from this A alpha. So let us take A1 from small a1 from A1. Let us take A2 from A half. Let us take A3 from A1 by 3 and so on. So let AN belongs to A1 upon n. As I said, A1 will be in A1, A2 will be in A half, A3 will be in A1/3 and so on. So let us take AN in this set for all n belongs to natural number. Okay. Now what we know? That means we will have a sequence, and what we know? We know that this X is sequentially compact matrix space, and here we have a sequence AN. Okay. So let us write, and there hence let me write here in bracket. This sequence AN will be inside X. It is for our understanding. So since X is sequentially compact, this is given by in the hypothesis, say by hypothesis, and we have the sequence AN in X. There exists or there is a subsequence let us take a subsequence AN suffix k k from 1 to infinity such that a and k will converge is convergent. So since it's convergent, there exists some a in x such that a and k will be converging to a. Right? A is in x. So since a and k is convergent, this implies there exists some point a in x such that a and k will converge to a. Okay, so mark this now. Now we have marked this statement. A is in x. Let us use this fact. Okay, so now what we know is we have a open cover for x. We have a open cover for x, and we have a point A in x. So let us use that fact here. Okay. Now since u alpha belongs to I, this is an open cover for x, and A belongs to x implies there will be a set where this A will be inside. Open cover means what? X will be contained inside union of this, and A belongs to x means A will be in the union. That means A will be in one of them, right? At least one of them. This implies there exists, say, alpha naught belongs to I such that A will be inside U alpha naught. Okay. And what we know? We know that this is the open cover. That means U alpha naught is open. So let us use that fact here now. So let us mark this also. U alpha naught is open and A is in this. And we have again, remember the fact that we are working in a matrix space. So in matrix space we have open balls. This is open, A is inside this, that means there exists an open ball. Okay, so since U alpha naught is open and A is in, and A belongs to U alpha naught, implies there exists some positive real number r greater than 0 such that ball around A of radius r is contained inside U alpha naught. Okay, so remember this point. And also what we have, let us take this r. Okay, let us mark this r now. Okay, now since mark all the points. Since we have a subsequence A and K which converges to A, right? This implies there exists some m belongs to natural number such that distance between A and K and A is less than for this r. Let me write. A and K converges to A for r greater than 0, and I am taking that r greater than 0 from here itself. Okay, same r. This is less than r by 2. So for r by 2 there exists some m. R by 2. But remember that r is from here itself. Okay, so distance between A and K and A is less than r by 2 for all K greater than or equals to m. Now let us choose n suffix l. Okay, so let us choose nl belongs to natural number for l which is greater than or equals to m such that 1 upon nl, this will help us, is less than r by 2. Okay, and using this nl, using this 1 upon nl, we will claim that, a set A 1 upon n suffix l will contain inside U alpha naught. And if this happens, then this will be contradiction to our statement in star. We said that this will not be contained inside any of this, and that will give us a contradiction. Okay, so now we have to show that this is subset of U alpha naught. So let's move ahead. Now, to show that, let us take a point in this set. So let a we have used. Say x belongs to a 1 upon n l. Our aim is to show that this x belongs to U alpha naught. Okay, and to show that this x belongs to U alpha naught, we will use that fact that ball around a of radius r is contained inside U alpha naught. Okay, so we show that x belongs to ball around a of radius r, and to show that ball around this x belongs to ball around a of radius r, we use a thing like distance. We will show that distance between a and x is less than r, and to show that it happens, we will use this fact. Okay, so let's proceed. Okay, now since we have taken a point in this set, since this L is greater than or equals to M, we know that distance between A and AL will be less than R by 2. Okay, because we have sequence. Okay, we have written this about the sequence. Now since, understand point by point, since diameter of a 1 upon nl is less than 1 upon nl, therefore the distance between x and a and l diameter, okay, nl will be less than the diameter, that is 1 upon nl, and 1 upon nl is less than r by 2. That is how we have chosen 1 upon nl here. We have chosen this nl such that 1 upon nl is less than r by 2. Okay, so distance between x and a nl is less than r by 2. So let us, and here we have proved that distance between a and l, I think this should be a and l. Okay, that's nl. Okay, so now we have distance between a and x. By triangle inequality, we can say that this is less than equals to distance between a and l plus distance between a and l and x. Okay, let me again state that this is, since l is greater than 0, the distance between a and l is less than r by 2. Just make the correction. This by triangle inequality, and we know that this distance is less than r by 2 plus this distance is also less than r by 2, right? And this is equals to r. That is, the distance between a and x is less than r. So if distance between a and x is less than r, this implies this x will belong to ball around a of radius r. And we have proved that ball around a of radius r is contained inside U alpha naught, right? And that's why we have taken that r. We have not taken any other r1 or r2. This is contained inside U alpha naught. That is, x will belongs to U alpha naught, and hence a 1 upon nl will be contained inside U alpha naught. And this is contradiction to star. This is contradiction. This is a contradiction to star. Okay, and hence let us conclude. Hence there exists delta greater than 0 satisfying. Let us not write all those points again, so let us do it in brief. Satisfying the statement statement of the theorem. That is, there exists delta greater than 0 such that the statement holds. And what is the statement? Statement is such that A, for any subset A of X with diameter of A is less than delta, there exists some alpha A belonging to I such that A is contained inside U alpha E. And this delta, which we have stated, this delta is called the Lebesgue number. Okay, that we will see in the next video. So in the next video, we will see what is Lebesgue number and related corollary, and we will prove one of the fact, that is, every sequentially compact matrix space is complete. So in the next theorem, we will prove that every sequentially compact matrix space is complete and every compact matrix space is complete. So stay tuned and see you in the next video. Till then, stay safe.